I want to go towards some more examples, which I've taken them from the paper. So we have a requirement here, which says that always all objects in a frame must exist in the next frame. We have a huge requirement here, but let's try to break it into parts. We have the always operator there because we have an always. That's what the red box corresponds. Since we are dealing with frames and the next frame, we basically want to freeze frame. So that's why we have freeze frame at time x. So we say that always there exists a set ID once at frame x. And the next part is if the next frame exists, that's why we have like a next operator there, the circle. So if the next frame exists, then there exists an ID2 in the next frame because we are dealing with the next frame here. And you say that in the next frame, the ID2 is basically corresponding to ID1, and then the class of ID2 is equal to ID1. So basically, you have made sure that if there's something in the previous frame at X, it's there in the next frame as well. Does anyone have questions?
One doubt. So in the next operator, we have defined like next and a variable if we have. It basically indicates if that variable is true in the next time step, right?
Mm-hmm.
So if you're saying next is true, then isn't it a function with, I mean, sort of a function?
So STPL inherently if there's an empty function there, how internally STPL operates is it assumes a frame or a type. Okay. So that's why the next frame exists. Thank you.
So I think, correct me if I'm understanding it correctly. So in the previous frame, you will have this O1 brackets D1. For example, in the previous frame, there is a bicycle, a pedestrian, and a car. So then you will say that, okay, cyclist is ID1, pedestrian is ID2, car is ID3. What if there are two cars?
So they have two different IDs.
And like every frame, you are assigning new IDs to each object.
Yeah, that's what the perception model is assumed to do.
So how do you, for example, the previous time, car A and car B was present. Like next frame, car A and car C was present. You will assign a new number to car C.
Yeah. So
how do you tell the difference?
That is the point here. So what the perception module does is that you're just not detecting objects. You're also trying to track them. Okay. Right. So if you keep track of those objects, it will assign the same IDs to similar objects from the previous frame. That's how an ideal perception model should function. For example, if you have a particular frame here where you have a pedestrian here, and then you have a car here, C1, and then you have a car here, C2. Then these are not going to disappear or appear, right? So what the tracking framework does is they're either going to go out of frame where they disappear completely, or they're going to keep moving forward. So whatever gives the IDs in the first frame, it's supposed to give you the same IDs in the second frame, because that's how you perform accurate estimation of all the objects in the system.
Okay, because my doubt is that in the previous example, the pedestrian walking along the street was disappearing like this frame and again next frame. I thought that is a problem existing in the current perception system.
Yeah, that is the problem that we're trying to tackle. Because if there's a pedestrian here, and if he's going inside the frame, if he's not going towards the border, he just can't magically disappear from the frame. The only two possible things are he either got occluded by an object, so he basically got covered by a certain car. Yeah. That could be one reason. Or the perception model is just not catching him. It could be any of the reasons. It could be the settings of the camera. It could be just a weird shape that the ML algorithm is not trained upon. So that's what STPL is trying to do. We're trying to create safety requirements over time for a certain perception model. So what an ideal module should do is it should be able to give the same pedestrian same IDs. If it's not doing that, it's unsafe.
And that is enforced by this logic here, right?
It's not enforced, it's like a metric. Think of it as a metric.
Oh, okay.
Yeah. So it could tell you how safe or how unsafe that particular perception is.
So I'll be the devil advocate, but so I understand the academic value of all of this, but what is the practical value? Like, how is it different from me sitting down and writing all these rules in regular coding language like Python? I mean, everything seems to be handwritten and defined. So what is the advantage of using this versus just putting it up and having a team of engineers writing all these rules? Because like all of this could be written by hand in Python or whatever language of your choice. Like, what is the value of all of this aside from academic value?
So correct me if I'm wrong. You're trying to basically say that why do I need to write 100? So if I just had to write like 10 to 15 specifications, I would handwrite them. And
Yeah,
just,
like I mean, I understand they're defining the logic, I understand the academic value of this, but I see absolutely no practical value of all of this aside from like having a team of engineers writing all these rules down.
so
Like I don't understand like how you can do like everything, like looking at the paper, it seems like there's no way of deriving things. It's like everything seems to be handwritten.
so
And like what is the advantage of using this over a team of engineers?
okay. So I have like three things that I want to address. The first thing is I've actually skipped that part so that it doesn't confuse everyone. But how STPL works is it's an extension of something called a time TQTL, time quality logic, and then it's an intersection of S4U. So what it basically does is it's an intersection and it's an extension over temporal as well as spatial operators. So you could certainly come up with, you could even write all of this in Boolean logic. But that will be very tough because you need to define in terms of temporal logics. So temporal logic, if you look at the first, if you look at the very first example where they gave the idea of the automatic transmission controller. So it says that if you have speed less than 120, always in 0 to 20 seconds, are you going to write? So first you have to simulate the entire requirement, and then what you're basically going to do is you're going to check it for every time step. And since you're dealing with a very high frequency of times, you're going to do a logic over entire time, or you could just write the specification here. So it's just the ease of how do we communicate with the computer to write these certain specifications.
And to give some context, the kinds of systems we're talking about are like, automobiles, spacecraft, military systems that are built by huge supply chains of subcontractors. So if I subcontract out an embedded system that is like putting the landing gear down on a Mars lander, me as the person who subcontracted that out, I want to be able to check that it can meet my specifications. And this gives me a language to describe that. And that's why you can't just say, well, the engineers will do it, because those guys will do it and they'll come up with kind of one way to have those safety specifications. And I might have a different view, and it might be just kind of one index off difference or something weird like that. And this gives everyone the same sheet of music to work off of in those big projects.
Just before next. And the second thing is this is available in Python and MATLAB, so you can use this instead of writing your own stuff.
For particular or practical use, is there any example? So when I see this, I was coming up with thoughts of, if you're driving a vehicle, the vehicle will constantly just stop and move, stop and move, stop and move, because of constantly the environment is chaos. So some people will hinder by some cars or some objects will seems to disappear by seeing those rules. By seeing those, this row will see the people that just disappear, or it's not following the rules, right? So it's not safe. So I just want to know that in the practical use. So the system, I mean, I understand the professor saying that in the very extreme cases, like for example, controlling the vehicle or controlling the Mars lander or some kind of a very special case that will need us to use this kind of a things to prevent damage or prevent like violation to some other things. But is that very useful in the practical use
So
in the vehicle driving?
So this was some recent work. So it's still in its, if you look at just STPL, and just, I mean, if you look, just standalone STPL, it's not, it hasn't gained much traction yet because this paper, if I'm not wrong, it was released in 2019 and then it was revised and submitted to archive in 2022. I think it's still under revisions in one of the journals. So this paper hasn't gained much traction. But if you think about it, we have we have the infrastructure to create good perception models, but we define good in terms of how well it will perform. But this, if we could somehow come up with requirements and say that this is what my perception module is supposed to do, actually, you could even evaluate the entire model and how it's performing over those requirements and see well how what is the degree of satisfaction or violation of my entire system.
So this does not, I guess we have the same question, like this does not enforce the system to do right away, like
Just like
Yeah.
giving it a suggestion.
like a metric to measure like some situations that the previous metrics cannot measure, which could cause catastrophic loss to the.
Yeah, and next lesson, we'll talk about systems that you can give it a specification. And then when you train the model, you can be sure that the model meets the specification. We'll talk about that next lesson.
Thank you.
So this example seems to be good. And I just wanted to talk about some more operators that were introduced in this paper. Someone mentioned that the next is very specific. And I think even Kirby hinted at the fact that you don't know what happens at the last frame. And ideally, if you look at the end of frame, the next would be a false. So this thing would eventually always, sometimes it would always lead to a false state, a violating state. So they introduced a weak version of next operator. And similar to next operator, they also have a previous operator which checks something on the previous frame. And then there's a weak version of it as well. That is what is covered in my next slide. And these are denoted by the following variables. So the next is a circle. Weakness is a circle with W in the subscript. The previous is the dot with the circle, and the weak previous is dot with the circle and the subscript. Moving on to one more example. So whenever a new object is detected, then it is assigned a class within 1 second. After which the object does not change class until it disappears. So what we're trying to say that at any point of time, if the perception model recognizes any new objects in a certain frame, it assigns a class to it within 1 second. And it does not change the class until it disappears from the system. Now, how you would formulate this is, let's look at like a broad specification. So we have freeze times at X. And we are saying that always, because we're dealing with all frames, we're saying that at ID1 at time X, we say that if class of ID1 is equal to 0, we follow a certain specification. So this part basically deals with a new object being discovered. And if it is already discovered, we basically follow this specification. So this is like the main broad structure. What the internals mean is that if you look at this sentence, whenever a new object is detected, then it is assigned a class within 1 second. So a new object has been detected here. How do you define this? You write constraints in terms of times and frames. So what these two conditions basically mean is the time passed is less than 1 second. That's why tau minus x is less than 1. But at least 1 frame has passed. So we are looking at the next frame. So we are saying that we are in time, we are less than 1 second. In terms of frame, we are at least moving forward in frames. We are not on the same frame. And then you say that you will have a new object and it is assigned an ID2, which is similar to ID1. and the class of ID2 will be greater than 0. And the second part is after this object does not change class until it disappears. So again, you have some the logic over frames. You are saying if it has the same ID, it basically implies that it does not, it stays the same over time.